we're now going to turn our attention to a very important concept in the solution chapter known as solution concentration expressions. It's important that you be familiar with the three major types of solution concentration expressions that you'll be asked to know in this chapter and memorize the definitions. Probably of any particular aspect of this chapter, solution concentration expressions will have the greatest application to your healthcare professions if that's the area that you're heading to. For example, many medications are delivered in IV form, a medication dissolved in solution, and being able to express the exact concentration of the IV, how much medication is present as dissolved solute in a given quantity of IV solution is very important. So again, memorizing these three different solution concentrations. The first is mass percent, or M/M percent. And this is going to look familiar to you if you remember the definition of mass percent that we looked at earlier this semester. Mass percent of solution concentration refers to the mass of the solute that is present dissolved per total mass of solution. And of course, to make it a percent, you have to multiply by 100. So mass percent, mass of solute divided by total mass of solution times 100%. The second concentration expression that you need to be familiar with is known as mass/volume percent, or M/V percent. This has a very important application in healthcare because the expression refers to grams of solute over total milliliters of solution. And as I mentioned with IV medication, you often are measuring the total volume in milliliters of the IV given, and you want to know how many grams of medication, grams of solute are dissolved in that. So mass volume percent, grams of solute divided by milliliters of solution. Notice the tight units here. With mass percent, units are not specified because it does not matter what mass unit you use as long as it is the same unit, numerator and denominator, so that it cancels out. But with mass volume percent, the units are specified. Grams of solute divided by milliliters of solution times 100 to convert it into a percent. And the third concentration expression that chemists are very familiar and comfortable using is known as molarity. Molarity, symbolized with a capital M. Molarity is defined as moles of solute divided by liter of solution. And of course, chemists are very interested in anything attached to mole amounts because that can take us right into a stoichiometry calculation, for instance. And we'll illustrate later that concept later in this chapter. So let's take a look at the first of these three concentration expressions and do some example problems with them. But before I begin, I should mention that all three concentration expressions listed provide information about the amount of solute dissolved in a given quantity of solvent. And that's very useful when you're working with solutions to know exactly how much solute you have present, especially since most solutions are unsaturated, therefore the amount of solute present can vary. So mass percent, the first of the three concentration expressions that you are responsible for. Again, defined as mass of solute divided by total mass of solution times 100 to convert to a percent. And we're going to do three different calculations involving mass percent. The first is a straightforward introductory calculation. How do you determine a mass percent of solution? So calculate the mass percent of a solution made by dissolving 32 grams of sodium chloride in 125 grams of water. So we're making a saline solution here. Healthcare term for a solution involving sodium chloride or made of sodium chloride dissolved in water. So let's take a look at the data. Our solute is sodium chloride, and we are told that we have 32 grams of it. Now, a common mistake is to take the 32 and divide by 125 grams of water, the solvent. But remember, mass percent has in the denominator total mass of solution, which means mass of the solute plus mass of the solvent. So if we're calculating a mass percent, we need to take the 32 grams of sodium chloride and divide by the total mass of solution, which is the 32 grams of sodium chloride plus the 125 grams of water, the solvent. So that will turn out to be 32 grams of sodium chloride divided by 157 grams of solution, and then multiply by 100 to convert to a percent. So double checking my calculation here, 32 divided by 157 multiplied by 100. Looking at my setup, I should have 3 sig figs for my answer. So rounding to 3 sig figs, I write 20.4% and then indicate in parentheses that this is a mass percent. Mass of solute over mass of solution. In our second problem, we're going to illustrate how we can use mass percent as a conversion factor. So all of the dimensional analysis skills that we've learned throughout the semester will be very important in doing solution concentration calculations. So the second problem refers to an antibiotic ointment called Neosporin, an ointment that's used to treat wounds where there could be a bacterial infection setting in because the wound is open and germs can get into the wound. Neosporin is an antibiotic that is used to treat the wound and make sure that an infection does not set in. So Neosporin ointment contains 3.5% by mass Neosporin antibiotic dissolved in the ointment to make a solution. How many grams of ointment must be applied to have 0.14 grams of Neosporin present on the wound? Note that you have to be able to write and use mass percent as a conversion factor in this setup. That's the key to the solution. So looking at the data, 3.5%, a mass percent. How do we write that as a conversion factor? Well, we recall that whenever you're working with mass percents, you take the value and place it over 100 to make a conversion factor. So 3.5%, 3.5 over 100. What mass units you use depend on the data in the problem. The mass units can vary as long as they're the same unit, numerator and denominator, so they cancel out. Since we're given data in gram units, it makes sense to use the gram unit in the conversion factor. 3.5 grams of Neosporin. And notice how important it is to label this. So I want to illustrate here that if we take the labels off, it is very difficult to know whether or not we use the conversion factor in its standard form or whether we need to flip it, invert it. All conversion factors can be used in their inverted form if necessary. And the only way to know how to use it is with the labels. So I'm going to write them back in. And make sure I've got my spelling right here. Right, so 3.5 grams of Neosporin over 100 grams of ointment. And now we're going to take a look at our starting data value. We need to obtain 0.140 grams of Neosporin on the wound. How much ointment do we have to apply to have the Neosporin present as dissolved solute in the ointment? A very straightforward conversion factor problem. Here is our 0.140 grams of Neosporin. I need to know how much ointment I need. So looking at my mass percent as a conversion factor, I see that I'm going to have to take this mass percent and write it in its flipped or inverted form. 100 grams of ointment over 3.5 grams of Neosporin. If I do that, I see that my grams of Neosporin cancel and I am left with grams of ointment, which is what I'm asked to solve for. Once we have the setup, it's very quick check on our calculator to determine the answer. 0.140 times 100 divided by 3.5, and I see that the answer is 4, but I need 2 sig figs with that answer, so I'm going to write 4.0 grams of ointment must be applied to the wound in order to have 0.140 grams of Neosporin present dissolved in that ointment. The third and last problem that I would like to do is what I call A-level difficulty. No fair doing easier problems and not presenting a challenging problem. The most challenging, in my opinion, type of solution concentration problem that I could give you involving a mass percent. So let's take a look at the question. What volume in milliliters of a 12.5% by mass HCl solution, hydrochloric acid solution, is required to have 0.640 kilograms of HCl present as dissolved solute? And I'm adding to the problem that the density of the HCl solution is 1.03 grams per milliliter. So lots of data in this problem, lots of data. And as I've warned my own students, sometimes I include information in a problem that is not necessary to actually solve for the answer, just to make sure a student understands the process and isn't just trying to arrange numbers and have units cancel. They have to really know whether or not the information is needed in the setup. So let's take a look at the data. You're given the mass percent of the hydrochloric acid solution as 12.5%. So we can take that 12.5% and write it like a conversion factor. 12.5 over 100. Hydrochloric acid is our solute, HCl is the solute in the numerator, and grams of solution is in the denominator. So 12.5 grams of HCl per 100 grams of solution in this particular concentration amount. We need to have 0.640 kilograms of HCl, our solute, and the density of the HCl solution is 1.03 grams per milliliter. So 1.03 grams of solution over 1 milliliter of solution. Remember that densities always talk about the mass of something as a ratio of the volume of that same something. So you have to have the same label, numerator and denominator. In this instance, we're talking about the density of the solution, so we will label it solution. So let's take a look at our setup. Our starting point is the mass in kilograms of hydrochloric acid that we need. So 0.640 kilograms of HCl. I'm going to go ahead and convert that into grams. If I need to use the density, density is in gram units. So I'm taking the kilograms and quickly converting to grams of HCl using the relationship 1,000 grams is equivalent to 1 kilogram of HCl. If I stop my problem right now, I've just calculated how many grams of HCl solute is needed. But I really want to know about the volume of the solution. So I am going to use my mass percent as a conversion factor. It will get me from grams of HCl to grams of solution. So mass percent written as a conversion factor, and I'm going to flip it again in this problem so that grams of HCl is in the denominator and grams of solution is in the numerator. So here is the mass percent written in its inverted or flipped form. Grams of HCl canceling, and I have just calculated how many grams of solution contains 0.640 kilograms of HCl. But I did not ask for grams of solution. I asked for a volume of solution in milliliters. Whenever you have a mass of a substance and you need the volume of that substance, or the volume and you need the mass, that is always a density conversion problem. So yes, we do need to use this density of the HCl solution in our calculation. So here we have grams of solution, and now I'm going to take the density of the solution, write it in its flipped form, so that I have 1 milliliter of solution over 1.03 grams of solution. If I look at the dimensional analysis, the grams of solution is canceling, and bingo, I am left with what I'm asked to solve for, milliliters of solution. So the dimensional analysis literally walked us through this setup and determined whether or not the conversion factors needed to be written in the standard form or in the flipped form. The last thing we need to do is take our calculator and do the operation. 0.640 times 1,000 times 100 divided by 12.5 divided by 1.03, and I look at my result, check my setup, see that my answer should have 3 sig figs, and converting into scientific notation with 3 sig figs, I have 4.97 times 10 to the third milliliters of HCl solution needed to have 0.640 kilograms of HCl dissolved within it. So 4,970 milliliters of HCl solution written in scientific notation with 3 sig figs.